Hello and welcome back. Our topic for this video is going to be chemical bonds, and there are going to be 4 types of chemical bonds I want you to be familiar with. All right, 3 of them are more biologically relevant. 1 is less biologically relevant, although I'll tell you how it does relate to biology. Okay, we've got covalent bonds, we've got polar covalent bonds, we've got hydrogen bonds, oops, and we've got ionic bonds. All right, so the first 3 there, the covalent, the polar covalent, the hydrogen bonds, okay? These are going to be the ones that we're most concerned with in biology, okay? I'm still going to talk about ionic bonds because ionic bonds are going to be important for doing things like making solutions, and solutions are important in biology just like they are in chemistry. But as far as the molecules I'm going to talk to you about in the next chapter, I want you to understand the difference really between the covalent, the polar covalent, and the hydrogen bonds, okay? Now, in terms of chemical bonds, all right, if you remember, we had our nucleus, right? And we have our electron shells. Okay? It's going to be the electron shells that are going to be essentially chemically active in making bonds. Okay? And in terms of our electron shells, all right, the first shell is always going to have 2 electrons. It's a little bit special. All right? The subsequent shells that we're worried about are going to have 8 electrons associated with it. All right? And typically it's going to be the 2nd or the 3rd electron shell that's going to be important in forming those chemical bonds for the biological molecules we're worried about, okay? Your chemistry professor will talk to you about chemical bonding at higher elements. I'm not so worried about that because in terms of the periodic table of the elements, most of our active biological, most of the elements that are important to us biologically are going to have electrons in the, it's going to be the first 3 shells that are going to be important, okay? So it's going to be the upper portion of the periodic table. And I think the periodic table I have in the PowerPoints, I've kind of labeled what the important elements are, all right? So our first shell has 2, 1, 2, 3, 4, 5, 6, 7, 8. Okay? So that would represent our 2nd shell. Okay? We could have a 3rd shell then, and maybe in our 3rd shell we only have 1 electron in that 3rd shell. All right? That's going to be the case for sodium. And before you email, I know I don't have the right number of protons and neutrons in the nucleus here. Don't worry about that right now. What I want you to pay attention to is what's going on the electrons in the outer shells. Okay? But in terms of that, that one lone little electron in the outer shell wants to have a partner. Because the thing about electrons is they prefer to be paired up. So in terms of that, to be more stable, atoms prefer and elements prefer to have a complete shell. All right? Now in terms of that, characteristic is what allows bonding to happen. All right? In terms of that outer shell, all right, for sodium, for example, it wants to donate that little electron that's in that third shell. All right? The other element that I'm going to pair this with is going to be chlorine, the chlorine atom. Okay? We've got a complete shell here, and just as time, I'm going to draw it this way. We've got a complete second shell, chlorine. Let me take that one off. Okay. Chlorine has 7 electrons in its third shell. All right. So chlorine really wants to have an electron there. All right. Sodium wants to donate. Chlorine wants to accept. Okay. That's how we get bonds made chemically. All right. Is with those electrons either moving or being shared between different elements. In the case of sodium and chloride, or sodium and chlorine, all right, that electron in the outer shell of sodium wants to go. Chlorine says, yes, I absolutely want that electron, because that then will complete its shell. Okay? And what we're going to do when that happens, when we lose an electron, what that does is it results in the creation of a positive ion. That's why I put that plus sign there next to sodium. Because in losing that electron, now we have more protons than we do electrons. And that's what makes something an ion. Okay? So in this case, it's going to be positive because it's losing the electron. All right? Over here with chlorine, I'm going to draw that negative. Because when chlorine accepts that electron, it has accepted an additional negative charge. So now that chlorine atom overall is going to have a negative charge because it has an additional electron. All right? And in terms of that, when I was talking about positive and negative, all right, when you've got positive and negative, those are going to attract one another. Okay? So in terms of our chlorine ion and our sodium ion, when you get that electron to move from sodium to chlorine, that creates a chemical bond. All right? And our chemical bond here is our ionic bond. All right? And I know I've got ionic bonds down at the bottom, but I want to talk about them first just to show you how the movement of those electrons can impact the different elements. Okay? The next video I've got, I'm going to talk in more detail about the covalent, polar covalent, and hydrogen bonds because they're more related to biology. All right? But in terms of that, because we've got positive and negative here, now those two ions hold together, okay, because of the donation of that electron. All right? Now this is not the strongest bond out there. It can be broken, okay, but the ionic bond is going to involve the complete donation of an electron to the other atom, to the other element, okay? So in terms of that, our electron shells are going to be important because our electron shells are going to dictate how reactive a particular element is, okay? Typically, when you have single openings or single electrons in outer shells, those are going to be your most reactive elements. So sodium, if you ever had a chemistry professor who brought in some elemental sodium, sodium is a metal in its element form, all right? And if your instructor put that sodium, elemental sodium, into water, it has a huge reaction. And that huge reaction is because of that electron wanting to leave that outer shell, okay? I'll post a video also, maybe if I can find one, of sodium going into water so you can see how big that reaction is if your chemistry professor is more responsible and didn't do that reaction in class in front of you, okay? But in terms of those ionic bonds, we're talking about donating an electron from one element to another, all right? Hopefully that makes sense. If you have any questions, please let me know.